Banach spaces, remember, were vector spaces with some norm so that they were complete. So these are norm vector spaces which are complete. For instance, all finite dimensional spaces, norm spaces on the reals are complete because the reals are complete. The continuous functions in the interval under the superior norm, that is functions from the reals to the reals, or it could be from some region or the whole of Rn to the reals, etc. It's from some close compact set to some other vector space. That's basically the most general case for these spaces. And then there are some that are not complete, like the continuous functions under the L2 norm. The continuous function is too small, so when we try to complete it, we get many more elements, so it's not complete. Here I'm missing some example. Let me repair this. Okay. So this is the definition, and we saw several examples, in particular in the space of sequences, small l square. Those are the infinite sequence where the norm is just the Euclidean norm, but the sum goes to infinity. The L infinity, small L infinity, those are the infinite sequence with norm where the norm is the supremum of all the elements, of the absolute value of all the elements. That space is called the space of all bounded sequences. And again, the norm vector space of continuous functions in some interval with the norm supremum of all x in the interval of the norm of fx. Here, as I say, you can change this absolute value here for some norm in some space, and then you will have the space of continuous function from this interval or some set in Rn to some vector space. It's the same construction. And we look at this space. This is the space of bounded sequences which are of compact support, namely they are finite bounded sequences. So they finished up to some point, they are zero. And this space is not complete because when you try to complete it with this norm, you discover that this element is in this completion, and this is the element that where this sequence where each element of the sequence is 1 over xi. Xi is 1 over I, and that's infinite. Then we look at how to complete spaces. First we show that this space, this bounded continuous functions, is complete. And we went through the proof because we are going to use it maybe on Monday or Tuesday, Monday probably. So we need to know this. And here is the proof, we went through the proof. And then we were talking about completing norm vector spaces. So in general, so this says that wherever you have a norm vector space, there is a completion. There is a completion that you build out of it. And usually what we do always is to say, okay, take this vector space, wherever you say the elements are characterized this way, the norm is this, and then complete. And just look at the completion. But sometimes the issue is to see what the elements are in the completion. For instance, you start some spaces with functions and you end up that the completions are no longer functions. So you have to characterize then what the completed space is and if it is good for you or not. So this is a task, but completing them is easy. So you can always say, okay, I'll take the completion. And that's what we are going to do always, take the completion. And we are going to see today how to work with the completion, with the dense set first, and then use that the space is complete to get definitions for the whole space of some functions, some maps. And then we start with the Hilbert spaces. Hilbert spaces are Banach spaces, so they are norm vector spaces where the norm comes from a scalar product, which satisfies the usual thing of the scalar product. And remember, for the scalar product, you have this Schwarz inequality that tells you that the norm of the absolute value of the scalar product between two vectors is less than the norm of the vector, the product of the norms. And this we are going to use. Okay, then we move on and show some examples. For instance, the space Cn is a Hilbert space if you consider this scalar product. The space of small L2, this is a space of sequences with this norm. So the scalar product in this case is this one. And you can see that this L2 space is complete. In the notes there is a proof of that. I don't know, I don't remember. Yes, we went through the proof here, so we know this space is complete. And this is important also because of Fourier transforms. We will see this today in a while. Then we look at the examples of the L2 norm. The L2 is Hilbert space, or the H naught. This is denoted like L2 or H naught. That's the space of measurable functions which are square integral. And the scalar product here is this one here. Oops. This here. And so the norm is this one here. And then we have Sobolev spaces. We are going to discuss Sobolev spaces. The Hm with m is an integer is a space where the norm is the L2 norm plus the L2 norm of the derivatives, the L2 norm of the second derivatives, and so on until you get to the m. So these are m derivatives. And the scalar product here is f with f, or if we put something else, f with g, say, gradient f with g and gradient f with g, and so on. This is scalar product. Basically, the scalar product we are going to use is either this one, or in some cases this one, only this one. But we are going to use a lot of the Sobolev spaces with longer derivatives, with more derivatives, that's for sure. And then we got some very powerful theorem, which is a rich representation theorem, and which has to do with closed subspaces. So we look at subspaces of a closed subspace of a vector space, a Hilbert space. And in the case we have a scalar product, so it's Hilbert, we can define, given the m, you can define the perpendicular. So these are all vectors which are annihilated with the scalar product where this one belongs to this side. So this is a perpendicular space. So in this case, is this space here, which is perpendicular. We are all familiar with the perpendicularity notion in finite dimensions. This is this analog in infinite dimension, and it works in a very similar way for Hilbert spaces, where we can introduce them. And so we prove the theorems that says that if M is closed, and therefore is a Hilbert space in itself, then the complement is also closed, and it's a Hilbert space on itself. And furthermore, you have that every vector x, you can write it as a vector z plus y, where z is in M, and y is in M perpendicular. And for that, we use we were approaching, we defined the distance between this point and the subspace M, and we were looking for the minimum. And we saw that the minimum is attained. So this set here is a minimal distance. And this is a property of Hilbert spaces. The distance you can define for any norm, but there are many cases where you don't obtain the minimal distance. This is only granted if the space is Hilbert. And then we prove that taking perpendicular to perpendicular, we don't get anything else. And then we got to the real important theorem here, this Ritz representation theorem, which is just a corollary. And this theorem, what does is the following. It says, okay, you have a Hilbert space, you define the dual of it. Here the dual are continuous. Continuous linear functions. On H. So a typical element of this is something that sends H to the complex phi, and phi is linear and continuous. Continuous means that it's bounded, so that you get the norm of phi with any vector is bounded by something that we call the norm of phi, which I will put here, C times B. So these are continuous linear functions. And what we can prove in this case is that given phi, there exists always a y such that this is true for all B. So that we can represent any element of the dual by an element of H prime, right? In general, given an element y of H, you can remember this xy, which were the elements of H prime, this belongs to H prime, given by y b. And this is bounded because the Schwarz inequality. This is a bounded linear function. So it's an element of H prime. So this belongs to H prime. What this theorem says is that the other way around, given phi belonging to H prime, exists Y so that phi is Y of, right? So it's the other way around. And we are going to use this theorem twice during the course, but further on the course. So now I'm going to give you a couple of corollaries, which also follow from that, but for some things you need more elements also, more tools, which we don't have here. One of the corollaries, we are not going to prove this, that every Hilbert space has an orthonormal basis. We don't know many, some of them we don't know. We know that there exists, but it's not something that you can construct in some sense. But you can prove that everyone has an orthonormal basis. Where we can prove something is in the following. We will take a Banach space, and in particular a Hilbert space, is separable if it has a dense subset which is countable with a countable number of elements.
Why this means separable in this context?
It comes from separability in topological things. It's that because you can build neighborhood of points which, given 2 points, you can build neighborhoods which are disjoint. And that comes from that, but it's a long story. Countable will be a better word for this. In a sense, it's because what it says, for instance, this is a base. Suppose you have this set here, consisting of all these functions. F of R as these are parameters, and these are R to the e to the minus s x minus t, and all of these parameters are rational, so they are countable. So you can separate the elements there. There is not a continuum. This is another interpretation. For the L2, for instance, you can take sequences which have only rational elements, and those are countable. So the L2 space, the L2, and most of the space that we are going to use are separable. I will say every one of them are separable. So dense means that, in particular, that you can approximate any element with element of this space, with a linear combination of them, finite linear combination. And there is a theorem there, which is the following: a Hilbert space is separable if and only if it has a countable orthonormal basis. So in this case, here we have orthonormal basis, but they can be not countable. Think of Rn. In Rn, we have the e to the I kx with k arbitrary. They are not in the Hilbert space, but you can think of them as a base, and they are not countable. What we know is that in L2 of Rn there is a countable base, but we don't know what it is.
How do you choose
Yeah, but it's not a base. Well, these are not a square integral to start with.
Yeah.
So they're not elements, even if you take them rational. So that's the main problem there. The space is separable, but the base you usually want to use is not a base because they're not elements of the space. But you know that you need they are infinite as a base to be complete. There is a set which is dense, which is something different than being complete. So a Hilbert space is separable if and only if it has a countable orthonormal basis, if S has a finite number of elements, and then H is isomorphic to Cn. This is simply because if I have a base, right, then any element I can write it as a sum of some vector of tuples of Cn times the base. So we have a map from the space to Cn, in one way or the other. So this space is the same as this. It's isomorphic. It's isomorphic here means that the map preserves the norm. That is, the norm of B square is the sum of the elements. Like that. So here you have a norm in your space, and here you have a norm in L2, or in C. In Cn. And in the case that it's infinite dimensional, then H is isomorphic to L2. So in the case of infinite dimensions, you have here the norm H, here the sum here goes to infinity. And so this space is L2, right? So in separable spaces, the structure is, the space itself can have very different things, but the structure as vector space is either Cn or L2. There is nothing else, nothing new. So how do we prove this? I'm going to go a bit on the proof of that. And so you take the S, which is a separable. This is the countable set, which is dense. And from that set, I remove many, many terms until I get a linear, until I get something which is, they are linearly independent and still span the whole set. So I take out many, many elements, but I still can get all the elements of S in the span, and they are linearly independent. And then I use Gram-Schmidt. You know Gram-Schmidt, you take some vector, take the perpendicular space to this vector, take some other vector here, take the perpendicular space to these two, take some vector in the perpendicular, and so on. And you build, and you normalize them, and you build the base. Right? So this is not a problem. You can do for infinite, for a vector space of infinite dimension. So the only thing you have to prove really here is that what you get is a base, so that you can describe any element with this set that you get from the Gram-Schmidt. And that's relatively easy, so we are going to go through this. So we get this set of orthonormal vectors, n of them, a finite set. not necessarily a base because it's finite. And we have this inequality, this identity. The norm of x in H is this quantity here plus the norm of the error. Think of that as, okay, I want to describe x as this sum here. And there will be an error, right? And this is error. So what this says is, okay, if I take the coefficients here of this representation, square them, sum them, the remainder to get the whole norm is just the norm of the error. In particular, if I can prove that this is equal to this, the error is 0. Okay? So at some point we are going to use that also. But for now on, think about this. And the proof is that is very easy. Just write B as this part, and W as the error, and then you take this, use the scalar product to divide these two things, and they are perpendicular. Use a perpendicularity of B and W, so that when you hit B and W, they are 0, and so you get this. It's trivial. And from that, it follows what is called Bessel inequality. So that if you are want to represent, one way of looking at this is, okay, I have a subspace. This subspace are all is the span of the xn up to n. So I get n, big N vectors. I get the span of that. This is a vector space. And I have a vector here, this vector. And I want to represent this, approximate this vector by this. So what I'm doing is just taking this in here. This is the vector B here, this one. And I say, well, there is an error here. This is the error, is this vector. This vector here. And what we are saying is that the norm of this vector is the norm of this square plus the norm square of this is the norm square of that plus the norm square of that. That's all. And what we are saying, this inequality, that's the only thing that says that this vector is less than or equal to this vector. No more than that. And if they are equal, it means that this vector is here. So we are representing them correctly. So now what we are saying is, what we want to prove with these inequalities is the following. Let S be a countable orthonormal basis of H. Then any Y in H can be represented this way, and we have that the norm of Y is this. Here, I like to talk about all these things, this theorem, because the following. This equal here, what it means. This is usually, for the infinite dimensional case, there is an infinite here, right? So what this equal means, imagine you are in functions. This is a functional space. So you want to describe function of x equal to some some sum of some coefficients, which are these ones, times some base, which is a function of x. And we write this in. And here we have x and x. And we think of that as that this number is equal to this number. Right? And this is not true. What we say, what it says is that this side with an n here tends to this, so that the difference between y and the sum, and we are going to see this, with to some finite number, this tends to 0 in the norm. Okay? But in this norm, for instance, if I take in the norm to be L2, the square integral functions, what I'm saying is that the function tends to this other one, norm, but it can be very different at some points. Right? There is no, if I want to evaluate in an x, it can be totally wrong. So these equalities here, even when we are treating functions, is an equality in saying that this is approaching this in the norm. Okay, the strong convergence, we say, is convergence in norm, nothing else. Yeah.
You said that if you look at a point, and exactly at a point, these two sides may not be correct. But in a neighborhood of a point, for example, is it true to say that these two sides are equal in almost every point of this neighborhood?
Yeah. For instance, you can say, you can take this error, let's call this En, right? The difference. You can take this En, this error, so this difference, and multiply by any other function, smooth function, compact support, say, and this will go to 0. So this is what is called weak convergence. Because sometimes some things can converge weakly but not strongly. So I can put functions here, things out here that they go to 0 for every 5, but in general they don't go to 0. Okay? For it, to give you an example, suppose you take any phi, so a phi like this, and you take e to the n something that is moving. So e to the n is some function like this. So it's a function's compact support, but it's every time you move the n, it's moving. Right? It doesn't go to 0 or anything. So when you have a phi here, this is phi, there is some n for which these two things coincide that is different from 0, but since this is moving, it will go away, and so this thing is going to go to 0 for every phi. Nevertheless, En doesn't go to 0. You understand the construction? Let me write it better here. So suppose I say I have a sequence of functions. These functions are some functions, compact support, of x minus n. So if 1 is like that, this is E1. E2 is something which is moved from here a distance once. So this is E2, right? Just move. So if I take any phi, multiply by En, integrate, this thing goes to 0, phi compact support. Right? But this En don't go to 0, they are just moving. They are the same thing which is moved further away. So the norm of this En, say, is 1. The norm of this is always 1. So it doesn't go to 0. But converges weakly to 0. En converges weakly to 0. Because if I put another function and integrate, it's always moving. Huh? So this convergence is weaker. But not for the reason you might think. Okay, you say, okay, this is almost the same as that. Then what I want is if I apply any function which is smooth of compact support, I should get this conversion to 0. And it does, but it can be happening something like this. That the error doesn't go to 0, it just simply move away. Huh? So let's clean this a bit. So we want to prove this. Where this means, as we said, the convergence in the norm, and this is inequality on the norms. So again, we say, okay, we have a map phi which sends every vector y into its components. This is in H, this is in L2, and what we are saying is that the norm in H of y is the same as the norm in L2 of the components, right? These usually they have the name Fourier coefficients because this was first done for Fourier series, and this is the Parseval relation, which is a relation between the Fourier components and the norm. Conversely, if you have some element of L2, Cn, an infinite sequence, then if you build this with the basis, this is an element of H. Right? So it's the map the other way around. So how do we prove this? Well, we have this Bessel inequality that says that this is less than this, less or equal, right? So let me call this thing An. This number is An. Now this An, when we move n, is a sequence. And it's a sequence which is monotonically increasing, right? Because it's bounded, and we are adding numbers here, so cannot go smaller. And therefore, it has a finite limit, so there is a limit a. So An tends to a when n tends to infinity. Now, if this sequence has a limit, we know that it's a Cauchy sequence. Cauchy sequence, remember, means that an minus am, if given epsilon bigger than 0, this thing will be smaller than epsilon if there will be a n bar such that this will be smaller than 0 for all n and m bigger than n bar, right? So now we do the following. Take, here it is. Define y's n to be this sum, right? That is the part of y that is in the subspace generated by the first n element of the base. And so we have this here is equal to this here. Why is that? Because suppose n is bigger than m, then this y is the sum up to n, and the other is the sum up to m. So the difference is the sum between m plus 1 and n. Right? And so we can compute this. So this is a number, and this is xj, which is our orthonormal vector. So when I take the norm of this is just 1, right? So what we get here is the square of this thing. So from here to here. And this is the difference between the a's. But the a's go to 0. This sequence converges, or these things goes to 0, so this goes to 0. And therefore, this thing goes to 0. Therefore, this is a Cauchy sequence. Therefore, since this is a Cauchy sequence, this yn converges to some y prime, right? Because it's Cauchy. So from here we conclude that this thing converges to some element of H. And so now what we have to see is that this element is Y. So what we do, we take the difference between Y and Y prime. So Y prime is the limit of this thing. So we put the limit outside and get this. And now we do the calculation. This y with this xn give me this. And from here, since I have xn and xj and they are orthonormal, I get this. So this difference is 0. Trivially. And so y minus y prime is perpendicular to the space generated by S. And since the space generated by S is all of H, it must be the 0 element. Huh? Okay? So we have built a base. So keep in mind that finding a base is not only finding the some set of orthonormal elements. You have to show that they are complete, so that when you can represent any element as an element of the space. And we are going to use it to discuss Fourier series and Fourier transform. So we need this result to use it there. And here, to finish, this is another example which is good to have another theorem, which is good to have at hand, and says let H be a Hilbert space, and let B1 of H be the ball of size 1. So these all elements whose norm is less than 1. That's a unit ball. Then B1 is compact if and only if H is finite dimension. So the ball that one thinks usually that if something is compact, it has to be a bounded closed set. In finite dimension that's true, but in infinite dimension it's not. It's false.
But you said that it is compact if and only if it is finite dimension.
Yeah.
Right? So why it is not compact in the infinite dimension case?
Okay. Remember that we prove in topology that if you have a sequence, a bounded sequence, so a sequence in some set, in a compact set, it has an accumulation point. Right? And I'll give you, the only thing I have to give you here is a sequence that doesn't have any accumulation point. Okay? So take L2. All the infinite dimensional spaces are isomorphic to L2. So if I prove it in L2, I prove for all. In L2 I take the sequence, which is En, is a sequence that is 0 everywhere, and it has a 1 in the n place. So this all here is 0. This is a bounded sequence, because the norm of those vectors are 1, they are orthonormal, and they don't have any accumulation points. You see?
Okay.
If you look some other topologies, in some other topologies, these are compact, but not in the L2 topology. For instance, you can take this base. This is similar to what we did just a moment ago. You take this base, right? And you say, okay, and take any element of the dual space. Continuous linear functionals on this in L2. So this is L2 dual, which actually is L2 also. Right? Then E to the n on any L2, on any element of L2, so this is En x, goes to 0 as n goes to infinity. Right, because these are square integrals. So the element have to go to 0. So when I go away with this element going further and further and further, it has to go to 0. So this sequence converges weakly in that sense so En converges weakly to 0. Right, so in the topology given by these weak things, which is not the strong topology, these things are converging. So the same ball for this other topology is compact. It's sort of, once you realize the things, it's not difficult, but at the beginning it's confusing. But we are going to use, mostly we are going to use only strong conversions. Where do you use weak conversions? Weak conversions you use with, if you want to do distributions. For doing distributions, you need to have a weak conversions. And we are going to use it, but for shocks and all these things, we have to use weak conversions. The solutions are distributions. Okay? Okay. So let's take a break until 10 after 10. Okay? 10, 10. Are there any questions on the other side? Nothing?
Professore, il video lì è per assistenza,
Sí, pero you can give me your names also if you want, so I can put you manually. I think I did it yesterday, but I will try to flag it yesterday to the class. If you can, yeah.
Vamos a pararla. Okay, we continue now. Now we are going to look at the Fourier transform or Fourier series first. Just very few things about the Fourier series, because basically Fourier series is a basis for a segment in the line, so an orthonormal basis in L2, so that's all basically. Somehow this is not working properly. One second, I will have to restart this. Okay. problem here. 1 second.
¿Qué pasa?
No, I cannot. I see this in here, and I try to enter, which usually is uses. Ah, okay. Now it's working. Sí. Okay, so now we are going to look Fourier series. Huh? I'm not going to say, as I say, not going to say much about this, but suppose you have an interval, 0 to pi. If you have some other interval, you just rescale things. And this is a base. Right? And how do you prove this? Well, let me see what I have here. Okay. Well, you prove this by showing that for any function in L2, the L2 norm of the function coincides with the Fourier coefficients. In a small L2. Huh? So you can this you can show. In the book there is in the notes there is a long way of doing this, but this is more direct. But if you want to see it, because in the book we show first that for some functions with enough smoothness you can, this thing is true pointwise, so you can represent the function as a series. Of the Fourier coefficients xn over square root of 2 pi, where the Cn are the interval between 0 and 2 pi, 1 over square root of 2 pi of f x e to the I n x dx. So this representation is pointwise if f is smooth enough. And then from there you can build all the things and prove a lot of more details and prove decay of the functions, etc. There is a relation between smoothness of f and decay of Cn. The more smooth this function is, these coefficients decay faster. Huh? So we know this. And one property, of course, that this base is useful, because if we take a derivative with respect to x, the f, and we put inside the representation, and assume that we can put the derivative inside, right, which is not totally clear, but for smooth things it is possible, then taking the derivative of this is minus in. So the Fourier coefficients of the derivative are this one, if the Fourier coefficients of the function are this. So, in general, what we are saying is that this in here, this base, is such that du to the I minus I xn to the x is minus in e to the minus I xn. So this base are eigenvalues of the derivative operators, with eigenvectors with eigenvalues in minus in. And so we know how to use this. For instance, if we want to solve this problem, right, the heat equation, same in one dimension, in some rod or some ring. Here we are thinking in a ring. So we have a ring like this, and we put some temperature here and see along the time how the temperature changes. So we assume at the beginning we put some distribution of temperatures. And so we assume now that we can do Fourier series in space. So with the space dependence we can use the base for the space, this orthonormal base. So this is the representation of this function of theta, and the coefficients of the Fourier coefficients depends on t. And then when you take this operator, this equation, right, you put these things inside this series, and you get this condition. So the second derivative is replaced by minus n squared, right? And with the minus that you have here, you get a plus. And here you use that this is 0 and this is orthonormal base, so these are linearly independent elements. So if we want this to be 0, this has to be 0. And therefore we have a relation between the Fourier coefficients at different times that says that the evolution of the Fourier coefficients satisfies this equation, which we can integrate immediately to say that the solution is the value of Tn at 0 times e to the minus k n squared t. And so if you express the initial condition, the initial temperature also in Fourier coefficients, you get these coefficients, and so the solution is this one. So you get the solution. So that's the way we usually use it. That's why this base is important. We could have taken any other base, but this base is important because they are eigenvalues of the derivative operator. And notice something in this particular case. We are going to see this in detail later on, but the new coefficient has this term here, which is an exponential. So for t positive, this in here goes to 0 very fast with n squared. When you increase n, this goes to 0 very fast. So this coefficient goes to 0 as n grows very fast. Right? And we say that this is related to the differentiability. So what we know is that as soon as you start solving this equation, evolving it in time, for all times bigger than 0, the solution is smooth. Even when t0 was not smooth. So if I start with, say, something like this, for any other time this is already smooth, or this is already rounded. And you can see, for instance, this because suppose you take p derivatives in time, right? So In space is smooth and also in time, because if you take p derivatives in time, this will drop this term here, which is a polynomial in n square, but you have this other term which is an exponential. So the exponential is going to win this term, so for n big enough, this term goes to 0. And so also the time derivatives are differentiable. You can differentiate the result. So the solution gets very smooth also in time and in space. Is clear why? So remember, we are in the setting where we are in the space L2, right? And the Fourier transform sends me, I have functions here, and in the L2 I have the Fourier coefficients. These are the E, I, N, F divided the square root of 2 pi. And this scalar product is an integer. So I need this thing to be in L2, namely when I look at the norm of Cn in L2, they should be the sum of the Cn, norm of the Cn, the absolute value squared, from n equal to 0 to infinity. So for this representation, we need that this sum is finite. And what we are saying is not only this sum is finite, but as soon as we start evolving, we get this exponential here with n squared. So if the coefficients initially were, say, like this, then when we use the evolve, these coefficients goes very fast to 0. Because as we grow with n, this term is very big. I mean, it's very small. This term gets big, so this gets very small. So all the frequencies go down to 0. We'll see this later on in detail. And we are going to play with solution of that. So this I describe here is how we see it in the sense of basis, because we are using here this is a base. Now I want to look at the same thing as a map. So we have this map we call F, say, or phi, whatever. Let's call it phi here. Phi is a map that sends functions to Fourier coefficients. So it maps H into L2. Okay? How is the map? Is you I have it somewhere. Well, here. Phi, I get F and I get the coefficients this way, right? So it's a map. And we know that it has an inverse. So we have a map with an inverse, and the inverse is continuous because it preserves the norm. That's what we prove in general, right, for any base. And another one property of this map is that if we take phi of a derivative of f with respect to x, this is proper from this map, not for all maps. Then this maps into I n C n, right? So this is I n of phi of f. This is, no, I don't want to put this. So every coefficient, you know, every coefficient changes like this. So the derivative operator, when you have a map, takes the coefficients, multiplies them by in each one, and give you some other coefficient, which is this one, right? So now we can say, okay, I want to map the equation. I don't remember what was plus or minus. Plus. No, minus, but not plus. I map the whole equation. And when I map the whole equation, this gives me the derivative of the Fourier coefficients that now depend on t, because I'm doing this for all t. Right, the map sends me to this, to minus k n squared. I don't remember whether it was minus. No, plus. I have a mistake here, I think. Minus. No, it's okay. This is. This is a minus. And this is a plus. So the maps give me, goes from this equation to this equation, right? And then I solve this equation, so I know that Cn of t is Cn of 0 times e to the minus k n squared t. And now, once I know this, I can go back with a map with the phi to the minus 1 and get equation for t of tx of theta is whatever, right? The difference, if I look at the map with this property, I'm using only this property. Once I know the map, I can do it. And I can do it even if this now is not an orthonormal base, right? Because all what I need is a map. So when we are going to see Fourier transform now, the base, these elements are the same. Now we, in the space we are from minus infinity to infinity. So these things are not any longer elements of L2 because they are not square integral. But nevertheless, we are going to have a map. A map now in the Fourier transform case, a map from L2 in the x, say, in the x to L2 in some other coordinates in the case, in the momentum coordinates. Right? And we are going to do this, we can do the same thing. But the important thing here is a map. It's not that this thing is a base, because it's no longer a base. So that's why I wanted to talk a bit about the map version here, because that's what we are going to do, or we do always in Fourier transform. So it's really the issue whether this is a base or not is not important. The only thing we need is a map. So when we look at the Fourier transform, we are going to look at the map, not because there is no base. We are going to use these bases in the middle, where they are really bases, but in general, we don't have any any base, so only the map. So we're going to see, so pay attention that we want to get this map. This is a Fourier transform, which is invertible. But to get to this map, we are going to use the basis, this base. So let's now go to Fourier transform. So we have this theorem. The transform is this one. It sends things from a function of x, say, in a L2 Hilbert space. This coefficient now is in Rn, and here we have this. So this is a function of lambda, and we want this to be defined for all lambdas in Rn. And this product is like this. And this map satisfies all these things here. So this map is linear. This is obviously linear because f enters linearly. It's continuous. So continuous means that in the norms we have a relation among the norms of f and f hat, and it's invertible. From L2 onto itself that preserve the norm unitarity, so the norm in L2 of the f hat is the same as the norm in L2. So it preserves the norm, that's why it's continuous. The inverse is given by this other map, which is basically the same as before, but we know all that there is a sign here, a sign difference. This is a plus, while here was a minus. And the thing we needed in the other case is that if we take if we take the derivative of f and apply the map, this is the same as multiplying the result of the map by I lambda j. Okay? So in the other case, we have integers here, in, and here we have lambda, a continuous. How do we prove this? Well, what we are going to do is we are going to use an argument. That's why I'm including the proof of this. It's because we are going to use an argument which is going to be used all the time, and so we need to learn it. We are going to use these times. Maybe I will mention a couple of times, but then we are going to use it as standard. So it's good to pay attention to it. So we first define the map for the C infinities. These functions here, this space, vector space, is all the functions in Rn which are smooth to infinity, and this zero means that they are compact support. So outside some compact set, they are zero. Here they are zero. So they have a compact support. I can bound the support by a compact region. So first we are going to see this map, how it acts from C0 infinity to L2, right? Why? Because here we can do all the calculations. And then we are going to extend this map to all the L2. We are going to extend it, and we have to say how to extend it. But first, let's do the calculations, and the calculations are always done in very nice spaces like this. So let's start with take some function which is in this space. So we know that there is a box big enough which contains this function. So let me draw this in a way, better way. So assume that for this f, we have a region here where it's different from 0. So we put a box here so that the function is included there. And the box is, the side of the box is 1 over epsilon. So we take epsilon small enough so that the box is big enough. So the cube here is n cubed CE. This is the CE. This is the omega, the region where the support of the function is different from 0, and this is a cube CE. So since this is a cube and the function goes to 0 there, I can use Fourier series to represent the function, right? So these are in fact the eigenfunctions in this region, right? They are weighted like that so that the L2 norm is 1. And so we have this, that for these functions we can do this calculation. Here I'm going to mark the scalar product because I don't see it very well. Here the scalar product is here, here, and I have a comma here. So with this is the Fourier transform. This is the Fourier coefficient, sorry. And this is the eigenfunction, right? And this, if we look at this, is equal to that. Because this integral here is this integral here. But not for any lambda, but just for the case. Which case? The case in this space. The k epsilon, big K epsilon, is this space that is defined here. So it's a net, right? It's all the vectors which are of this type, pi, epsilon, and p, where p is an integer. So Ka is a space of all these points. Where this distance here between these 2 points, this net is pi epsilon. When epsilon goes to 0, so the cube becomes bigger, this goes to 0. So we get this relation. That this in here is just this calculation here. And this is just the Fourier representation of f, so this is f of x. in the Fourier series representation. And so, since this is a map in this Fourier series representation, this is a map for an L2 to L small L2, we know that this in here is equal to this in here. That is, actually we don't need to do this calculation, but this is defined like that. And since this function is only supported in this space, in this cube, it's the same as this here, and this here is the same as this, and this, when we use this formula, is just like that. So now, if we knew that this function is continuous, then what we have here is the Riemann approximation of an integral, finite Riemann integral. So this is the volume element, and this is a function, so we are summing over all these things. So if this were continuous, this converges to the integral of f sum lambda square dn lambda. And here this is also converges to an integral, and this converges to the integral that we have upstairs. So 1 over 2 pi n over 2 integral of f of lambda e to the I lambda x dn lambda lambda. Okay? So what we need to show now is that the f is continuous. And for that we look at the derivative. We look at this thing. The supremum of f hat k, the derivative of fk. If we know that this is finite, then we know that the derivatives are bounded, and so the function is continuous. So this is the same as this. What we have done here is fk with respect to k. When we look at the formula, right? We have to use this this is fk, right? That's in here. So when we take a derivative with respect to k, it's the same as taking bringing down an ak here. So we get the minus ixj here when we do the derivative with respect to k, and we get this. Right? This is this integral. It's less than this integral. But f is compact support and smooth. So this in here is bounded, right, by the integral of that thing, and that's fine. It's clear? And so the integral converges. So what we now know is that we have a map f from C0 infinity to L2. That keeps the norm the same because we have this relation. I mean, this goes to that. So we know that we have the L2 norm of L is equal to the L2 norm of f hat. Right? We have that. For all functions which are C0 infinity. So now what we want to do is to extend this F and get a map from L2 to L2. This is an extension. How do we do that? F is continuous, so let's put it here. This discussion is this one. I'm going to just do what I did up here. This is this discussion. I'm just going to do it with some drawing. So imagine now that we have an F which is in L2. And we want to extend this map, so we want to find what is F, the big F of F. What we do is the following. The C0 infinity functions are dense in L2. So if you take the completion of that, you get L2. Okay? So what we are doing is, okay, we can approximate F as the limit of some functions. Let's put an, I think I use capital things here. The limit of some functions to F, where these ones belongs to C0 infinity. Okay? So I want to get a Cauchy sequence of these functions. Okay? So they are converging this, so they are Cauchy. So Fn minus Fm. If I look in L2, this goes to 0 as n and n go to infinity. Okay? Now, for each one of these Fn, since it's in this space, I can have the F hat of n, the corresponding. So I can send them by the map, right? And they have the following property, namely, if I take the two of them and take the L2 norm in the Fourier space, this equals to Fn minus Fm, because the map preserves the norm, right? And these ones were Cauchy, so this tends to 0. So these are Cauchy. Therefore, since L2 is complete, they converge to some F sub hat. And so now I say, okay, F tilde, F, big F of F, is defined to be F hat. Okay? And so this is the way you extend things. So the trick, this is when people start working with these things, particularly if they are not mathematicians like we are, it's very confusing because you start doing calculations assuming that you can do calculations, integrate things, etc., take derivative, etc., and you know that in the whole space those things are not possible, because in general you cannot say, for instance, take a derivative, right? We use that Fk was continuous. In general, it's not going to be continuous. It's not going to be bounded, etc., because it's in a bigger space. But we do all the calculations in a space where we can do all the things and then extend the result. Of course, to extend the result, you need to have a bound, something like we have here. Maybe it's not equal, but maybe something like that. But you need something like this, so that you From here, from a Cauchy sequence here, you get a Cauchy sequence here. And then you know, because the space is complete, that there is something, and you put this something on this side. Okay? But this usually is not explained, so that's why I want to take some time to explain what is going on here, because otherwise people get, at some point one gets very confused because one doesn't know what the space is, etc. There is a first point where one is naive and think that things are differential and so on, they're nice, and you do all calculations, you never pay attention whether they are possible or not. Then there is a step where you realize that things are not smooth, etc. And then you start worrying about taking derivative, etc. Everything, you don't understand how to do calculations. And then you realize this thing, and then say, okay, this is the way it goes. Okay? But it goes like this. So now we know Fourier transform, and we are going to use it in the next hour. So let's stop now and resume at 11:10. Questions on the other side? Nothing? We continue now. Now we are going to see some Sobolev spaces, some properties that we are going to need for dealing with differential equations. Huh? So next hour, so this hour I'm going to talk about that, and then Pablo is going to start discussing some way of solving ordinary differential equations. The first approach, so we are going to warm up for the next week. So now it's working this thing. So now we are seeing some basic properties of Sobolev spaces. Remember, a Sobolev space is a Hilbert space with a scalar product. For instance, the HM space with M is an integer for now is the sum on K, sum on J, etc. from 0, actually not 1 here, of some derivative here, some derivative here, etc. So basically a typical, say, H2, the product in H2 will be f of g in H2, is going to be the integral of f complex by g plus the gradient of f scalar, the gradient of g, plus second derivatives of f, all multiply in sort of a Euclidean product with all the derivative of g. So that will be the nx. The scalar product in the H2 Sobolev space. And since we know that we can go to Fourier transform, be transformed to the space of momenta, we can transform this H here. For each momenta, we lower an I lambda, and since we are taking the absolute value, and in one side the bars, and in the other side without the bar, the I bar times I is 1, So we can forget about the i's, and we get these things. And so what you get is g times this g of f of lambda and f of j of f of lambda hat and g hat of lambda times these factors. So this is a product of the lambdas to some power. And these are now the norms in the Hilbert space. So we say that f belongs to this space if the Fourier transform decays so fast that this thing here is square integral. This thing here is what we have here. So if we know that, we can do a generalization and say, okay, now I'm going to take S to be real, and now I'm going to say that I have this scalar product. F of g in Hs is equal to the Fourier transform of f and g times this factor here. 1 plus lambda squared to the s over 2. Right? For m positive integer, this is equivalent to that because we always can bound this sum that we have here by something with the highest component here and the highest component here. No? We can bound these two constants. So to do that is the same. To have this norm is equivalent to have this other norm. And this other norm is simply to work. And actually this norm is nice because these norms comes from, in Fourier space, the Fourier space of the Laplacian, actually minus the Laplacian of a function, the square root. So that will be this operator to the s over 2 applied to the function in the real space. So these things can be done also, but it's handy to have this way of expressing. So we are going to generalize and define Sobolev spaces this way. And you might say, well, why do you need to do that? Because we are going to see later that there is some situations where you need a half integer s. With integers, with m's, you cannot do that. So we need to lower this to allow for rational, at least rational numbers. So we might as well just define for everything. And then we have very trivial, right? The following statement. If S prime is bigger than S, then all the elements of H prime, of Hs prime, are inside the space Hs. That's because S prime has a bigger coefficient here, so if things are in S prime, they are also here. They decay in S prime, they decay faster than what you need in Hs, for instance. Therefore, the integral in Hs of the norm is finite too. In particular, if things are in S bigger than 0, then all the spaces Hs are subspaces of H0. And remember, H0 is just L2. So what we're having here in the Sobolev spaces, at least for S positive, are subspaces of L2, complete subspaces. Now but here I use S in general, and S could be negative. So instead of having something multiplying on the numerator, they are in the denominator. What are these things? Look at this map. So you take an element of g to the minus s and define this map. Phi g applied to f is equal to g, the hat, the transform of f and g in h0, and then you can have, you multiply them by this term here and this term here, and so this thing, if this thing is in hs, this is going to be finite, the norm of this, and the norm of that is going to be finite if g is in s, in minus s. Huh? So we have this relation here. So this is a function, linear function, which is bounded. So it's a linear function. This phi goes from hs, h minus s, to hs. For each element of s minus 1 produce a bounded linear functional in hs. So these elements are in hs dual. Right? So the space of s negative are the duals of the space hs. So this is h minus s. It's a dual space. So this is a relation. And this is nice because we can use this. Suppose we have something in H1, we know, okay, the functional, linear functional, you can produce them using some g in h minus 1. So this is a natural setting for many things, for having functional, so we are going to use that. Okay. Here is another property of Sobolev's, and it's very important. This is why Sobolev spaces are so important in principle. And it's the following. If you have m, which is smaller than s minus n to the 1/2, where the n is the dimension of the space, so we are in Rn, then this space is contained in Hm. So all the elements here are m times differentiable with the m derivative bounded. M times differential. So since in these spaces, if f is big enough, they are nice. I mean, you can write this as s bigger than n plus n over 2, right? So if you want something to be 3 times differentiable and you are in 3 dimensions, you have 3/2. So this is 6 9/2. If s is bigger than 9/2, you know that is your the elements in hs 9/2 are 3 times differential. So how do we prove this? Well, we just prove for m equal to 0, because for the other case you just take derivative and increase this both sides. Is by induction, basically. And so we want to prove this inequality, right? Because this inequality here, it will say that if, okay, why do we want to prove this way? Because if we have this, if we can prove this for C infinity functions, and we are going to do that. If we can prove that for C infinity functions, then we do as we did before. We take, for any function here, we take a Cauchy sequence of nice functions, converging to this f. And since this is Cauchy and we have this inequality, then this is going to be Cauchy here, so we are going to get an element here. And so this way we know that the elements correspond from one space to the other. So how do we prove this? Okay. The norm in C0 of a function, remember, is the supremum over all x in Rn of fx. Here we put the supremum and not the maximum because this is a non-compact space, right? So we are not sure that we get the maximum. So we have the supremum. And here we use, instead of fx, we use a representation in Fourier transform. Since this f is smooth, we can use this as a smoothing, and this representation is okay. Actually, here I'm saying that, assuming something that we didn't see, that if we have an f which is smooth, then we have a f hat that is smooth too. And so this representation is okay. But here we can say the other way around. We say, okay, we are going to do this for all f such that f hat is smooth. Work with these ones, and then do Cauchy sequences in this space at the end, and get the result in the complete space. So this is not really an important point. So we are assuming that this is smooth enough so that this integral is valid for any x, and this is the values of fx. So we can substitute this by this in here. And this, since the norm of that is 1, the absolute value of that is 1, we can take it out, and we have this inequality. So we bound this by the absolute value, which is 1. So we get this, and here we multiply and divide by this factor. And now we use Schwarz inequality to write this as the norm of this part of this part and the norm of that part. So we take this to a square, so this is the norm of that, and the norm of this part. And if this norm is finite, this is HS norm. So we get this when this thing is finite, if this is finite. So this plus this thing is the constant C. When this is finite, well, what we have is this norm here is the integral over 1 plus lambda squared to the s differential n of lambda, right? This is the integral, this one, the norm. And so this is going to be finite if, right, if you are writing angles, this is going to be, there is a lambda to the n minus 1 here, the lambda and the omega, and so you have a 1 plus lambda squared to the s, and you need this to be, you know that the one that starts to be bad is 1 over lambda, because that's the law, right? So this has to be, the coefficient here has to be smaller than 1. So what we need is 2s plus 1 minus n, which is the coefficient upstairs, has to be smaller than 1, right? So 2s minus n has to be smaller than 0, and so s has, I'm doing something wrong here. I want this. I want this is bigger, this alpha bigger than 1. So I have the other way around, sorry. I want this to go to 0 faster. So this is bigger than 0, so s bigger than n over 2. Huh? So this was a condition. And so if s is bigger than n over 2, then I know that this function f is continuous. If s is bigger than n over 2 plus 1, I know that the function is continuously differentiable, and so on. It's clear? Any question about that? It's a simple calculation. In fact, if you want to know these values, you just do this. You check that this factor has to be finite. The norm of this has to be finite. What else do we know about Sobolev spaces? Other important results, we probably will not use it, but I'm just describing this. Suppose you have a region, you have functions defined in this region, and you take a plane here that goes through the region. And so this plane cuts the region here. And then you can say, okay, suppose I have a function in the big space which is in HM. In the well, I'm doing the. Let me do this case first. Suppose I have a half space. So functions that live in this side. And I want to see in what Sobolev space are the functions, the trace of the function, which is defined as the values of the function in this, for x equal to 0, in this plane, in which Sobolev space is this function. So if I have a function, say, in this space here, in the positive half plane, half a space x positive, I want to see this function, which is are the values of the function here, restricted here, in which spaces. Well, it turns out that if f is in Hm, then the function in the boundary is in H minus 1/2 of the boundary. The calculation is very similar, just have to do Fourier transforming in one less dimension and play a bit and you get this. But you lose half derivative, basically. So this is why we need these non-integer values for m, for s, because when we go to the boundary, we lose half of derivative. And we don't want to just lose one derivative, because we could say, okay, the map goes to n minus 1, and this is not okay. So this is a real thing. So that's why we need s at least half integers. So the restriction for in the space of one dimension less of something smooth, right? You can deform this. You can say, okay, I have a region, a ball. I have an f here, and what is the value of f in the boundary? The trace just is the restriction of f to the boundary, and in what space is, and I can find that if f belongs to Hm in the interior, then the trace of f, that is the values on the boundary, are in Hn minus 1/2 in the boundary. And this is if the boundary is smooth. This is important. If I have a boundary which is not smooth, I might lose these properties. This is repeated here. So this is a trace theorem. It tells you, for instance, where is this important? Suppose I want to solve the Laplace here, Laplacian u equal to f in omega, and I want to give some boundary conditions. U restrict to the boundary is equal to g. So what I have to give here, this g, suppose I find that the solution is f is so nice that u is in, I want u in H2, so that you have up to second derivative square integral. Then I need to give j to be in H 3/2, right? At least, so that if I give an j which is of lower differentiability than this, I will not get this this f in H2, because when I try to paste it into the side, it will not be possible. So that's why I need this condition. Okay, let me go through this quite quickly. It's not really, it's the last part. It's not really very important. Well, actually it's important, but I don't want to go to much details now. After me, Pablo is going to talk about the first things in numerics, and with Julia for the last hour today. So this is related to the following lemma. Let omega be a region in Rn which is compact and with a smooth boundary. So this is the setting we were just referring before. And now we have a sequence in this space. What is this space? This is a space H1 0 of omega. In omega you can have two H1 spaces, the one without the 0 and the one with the 0. The one without the 0 is a space. H1 means that you have the square, the first derivative, so the norm in that space is just the integral over omega of u squared plus gradient u. The norm in this space is the same norm, but for this space we take any function u belonging to C infinity. So any function, say for instance, if you are in one dimension, you take any function, say this function, in this interval, this is omega, any smooth function, and you complete the space. You take this space and you complete with this norm. And then you get the H1. This space here is where you complete the functions with functions that are 0 in the boundary. So this function, for instance, all these functions, but they have to be 0 on the boundary. When you complete in this space, so let me call this u belongs to u0. So are functions that go to 0 on the boundary. Then you don't get the same space, you get this space. Right? So it's a smaller space. So this is strictly contained in this. And this is the space we are going to use a lot. And so this lemma says, okay, if I have a sequence here that is bounded, there exists a subsequence that converges strongly, so in norm, to H0 in L2. And that's what we call that this map from this space to this space that assign every function here to a function here is compact. So if you start in a ball, because we are considering sequences that are bounded, in a ball in this space, there will be a subsequence that is convergent in this one. So there is a limit point, an accumulation point, right, in this space. So what we have is, we have this omega compact, and we have a sequence here of functions, say in the space H10, in this space, let me use another color for, this is a space, it's a draw of the space. We have a sequence here, which is bounded, so it's in a box here, in a strong norm, because this is the H10, so this knows about the derivative of the function. If we have something bounded here, then in the other norm, in the H0 norm, the L2 norm, this sequence has accumulation points. So if we look at at some points here in a neighborhood with respect to the say there will be points u such that in a neighborhood when I take some value of the sequence, this is going to be less than epsilon in the H0 norm, not in the H1. And so there will be a subsequence, so I will take all the elements with have this property, and since it's accumulation points, it goes and goes and goes near this point, so I can take all these elements and make another sequence. And this subsequence is going to be Victor convergent in this space, not in the original. So this is a way of picking one element, but just having this property. So I have if I find a bounded sequence here, I know that there is an element in a space which is bigger, for which this sequence converges. There is a subsequence that converges. And to prove that, we use this lemma here, which is as follows. You can show that the norm of any function in a cube of psi d is bounded by this. So here you have, this is the norm in H0, so this is the L2 norm, so this here is just the integral of u squared d nx is bounded by the integral of the value of u. You see here there is no square, the square is outside, and 1 over the distance, so this number goes to 0, this part goes to 0, like d to the minus 1. And then there is another piece that has t squared times the norm of the derivative in h naught. So this is just the integral of gradient u, scalar gradient u. So you have a bound, this is bounded by the value of u integrated square plus the derivatives square. Imagine if you don't have this piece, you will say, okay, this cannot be true because I take a function which is 1, so this integral is the volume of my omega region, and this side is 0 because here I have 1. I have 0. I use u is equal to 1, so this piece is 0. So in that case, I need this part. So this part here is essential, otherwise it's not true, because we are allowing any function, including the constant. So we do the calculation, as usual, with functions which are smooth. So in particular, we take u to be C1. We take the difference between these two values inside omega, and use that this difference is just an integral over the derivatives. So suppose I have these 2 points, this is x and this is y. So if I am 2 dimensions, I know that to get this point from this point, the value of u, I can get this value, integrate like this along x, one axis, and then integrate like this along the other derivative. So in general, here you see I'm integrating over different derivatives going from x to y. I'm just doing this work. So this is nothing more than this. And now we take the squares and use Schwarz inequality in this side. So we take the squares, we get this square minus twice the real part of this. and then we get, here we use a Schwartz, so we multiply this by 1, and so we get this with the square. And now we integrate over x and y. When we integrate over x and y, this gives me the sin I want here, and this again, so I have 2 times this. And since I'm integrating this on x and on y, I get the volume of the box when I integrate over y here and over x here. And from this side I get this one, and from that one I get this factor here squared, right? Because when I integrate by with respect to x, this gets out, and when I integrate with respect to y, this gets out, and so I get the integral of u squared. Now that's easy. So now we have to show this property here. Okay? But actually we already are very late. I led you to look at this, the proofing. It's not difficult. It's just an inequality. So if you have a question next Monday, we can discuss it. I hope you can take the weekend to look at the things, and on Monday morning we can answer questions. We can take an hour or so to answer questions you might have, doubts, etc. Okay? So we'll cut now, and 12:05 we can start. So let me cut now, because otherwise Pablo is not going to have enough time.